Sensitivity and specificity are important in evaluating the accuracy and predictive validity of assessment tools, the accuracy and predictive validity of diagnostic and prognostic tools. They're also important in detecting effects or differences between groups. So sensitivity is the ability to detect a condition or an effect when it is present, and specificity is the ability to rule out a condition or an effect when it is not present. So here again are the definitions of those two terms, and here's a graphic representation of the possibilities here. So in the top row we see a condition, and these two columns represent whether the condition is really present or absent. And then in the bottom two rows we see the result of a test or a research result showing a negative result or a positive result. And the possibilities here are shown in the middle four cells. So we could have a true negative result, meaning that the condition is absent and our test result is negative, so we're correct that the condition is not there. We could have a false negative result, meaning that the condition is present, but our test turns up negative. We could have a true positive result, meaning that the condition is present and our result is positive. Or a false positive result. The condition is absent, but our test is positive. So these are the possibilities for sensitivity and specificity. Whatever our test result is, we're going to make a decision. Okay? So here we have test results arrayed on the horizontal axis. Okay, and let's say this is a result for a disease, and positive results to the right of the horizontal axis mean that the disease is present, and negative results to the left of the horizontal axis mean that the disease is not present. And then you have two populations represented by two bell-shaped curves. The one in the left with the solid line outlining the distribution is the population in which the disease is really not present. And the one on the right, represented by a dotted line, is the population in which the disease really is present. Now we've got three different tests that have different levels of sensitivity and specificity. Test A suggests that any result above that line is going to be considered positive, and any result below point A will be negative. So this test is 100% sensitive, meaning that it identifies all the true positive cases. But it also identifies a lot of false positive cases. In fact, half of the negative cases would be identified as positive. Now jumping to the right, test C is completely specific because it rules out all of the negative cases. So that's 100% specificity. But it also has many false negative results. So many of the true positive cases are ruled negative under test C. Test B is the most accurate. Now it makes mistakes in both directions. It has some false positive and false negative results, but it also is the most accurate in that it is the one that balances sensitivity and specificity. Now, a main point here is that mistakes will be made in these kinds of classification systems, and researchers and the public need to make sure that their decisions about sensitivity and specificity balance relative risks and harms of diseases and treatments. So again, positive results are to the right of the decision threshold in this diagram, and negative results are to the left of the decision threshold. These decisions, represented by A, B, and C, are sensitive or specific depending on how many false and true results they obtain.